I feel bad.
Are
So
we going
back
to
to
have a
this
question like this on the test?
It's relevant to the test, yeah,
Right.
because it's looking at the stability of those.
Would you ask which hydrogen's the most
More acidic? Absolutely.
Because that makes more sense than what this is as. I'm like
Isn't that what it asks?
Yeah, but it says it in weird, like,
Oh.
chemistry stuff, and I'm
Chemistry words.
confused.
Oh. Well, you can see exactly how I would phrase it. Why is that more acidic than that?
Clint Eastwood.
There you go.
Oh, yeah, he is old.
So if we went through and looked at this structure, after it got rid of its hydrogen, we'd have the negative again. Can we do resonance in this structure?
No.
No. So with the cyclopentadiene, help, help, I'm dying. We have an aromatic stabilized conjugate base. If we have a more stable conjugate base, what does that mean about the acidity?
Stronger.
It's the stronger acid. So this one becomes a stronger acid because the conjugate base is more stable. Does that make sense?
Mm-hmm.
So we can go through another EAS reaction. Did you want to see this? So to start off, we need to find our electrophile. Aluminum in this case is special because it's happy with 6 electrons. So that means it's sp2 hybridized, it has an empty p orbital. So what we can do is take electrons from the chlorine, share them across, and we can generate this species. The aluminum just gained electrons, so it's negative. Chlorine just lost electrons, so it's positive. Chlorine doesn't want to be positive, so we can shift some more electrons away, and what we end up finally generating, which we'll draw down below, come on, will be our electrophilic carbon now. I have to zoom in a little bit better there. Once we have the electrophile, we can then react that with our aromatic ring. So we can go through and take our electrons from the aromatic ring and share. Mm-hmm. And we can generate the product of that. It's drawn very crooked. Let's try that again. Leave our double bonds. Put in our group. Our last carbon over there ends up being positively charged because it lost electrons. We're going to want to try and stabilize that as best we can, so we can find our pi electrons, push them over. Since we're only moving pi electrons, we're looking at resonance, so we technically need that double-headed arrow. We've got now our positive charge up top, double bond. Again, we can move more electrons, bond to bond. Oops. And we get yet another resonance structure. I'm going to draw this one a little bit more crooked. We got our positive charge over here. One of the things that I didn't draw on in each of those structures was the extra hydrogen that ends up getting substituted for. So we can add that now in each structure. If we look all the way back to the beginning, we've got the hydrogen there. We still have that hydrogen here, and here, and over here. And the way we've shown it in class is from one of the cases where the positive charge is close by. So we can go in, take the electrons away from that hydrogen, and form our double bond to finish off our mechanism. Okay. The reason I drew it out like this, we'll see in a second here. Again, a little bit crooked. And we get our final goofy-looking product. Yes? Mm-hmm. We don't have to have the electrons move in that last structure. Okay, so if we went back, for some reason we moved too many electrons to begin with, and say we ended, I'm going to erase our arrows here, and we want to show how we can get to our final product from this structure, from our middle one. Well, we can still take those electrons out do our arrow, but now this carbon has too many bonds. So what do? We'll move it up. And what's the result?
Same thing.
The exact same thing. We could still do it even from the other side. We could even push it really far around the ring. So from our last resonance structure, we could go through and push this direction, which is really excessive, but it works just as well. Okay. So you can do multiple arrow pushing. We try to pick, like we did in the last case here, with doing one arrow at a time. So there's less things happening in each individual step, so it makes it a little bit easier to understand. Make sense? More questions about it?
No.
These structures are resonance structures. Come on. And here, if I ask for a complete mechanism, those resonance structures must absolutely be drawn. You'll see these referred to as either resonance. You might also see them referred to as sigma structures. Okay. And if a mechanism is asked for, you absolutely must show those resonance structures. That is critical to the mechanism.
Okay.